Welcome to a lesson with Dr. Powell. Let's take a look at the idea of well ordering on a set. So given a set S, we can think about trying to list out all the elements that are in here and putting it in a list, in an ordered list, such as with the first position, a second position, a third position, and so forth. And a well ordering intuitively is the idea that we can do this with all the elements in the set. I mean, this doesn't seem likely. If we look at like the set of everything in an interval in the number line, and we're looking at maybe a sequence like a half, 3/4, 5/6, 7/8, and so forth, this list goes on forever, and we has different positions in it: first, second, third, and fourth, and fifth. And it definitely will touch, not even touch even a hair of what really is in this set. So, how in the world can that list be extended to all of this? Because it already goes on forever. Well, the idea is that we think about everything that we can list out as set B, and all of these have a particular ordering and something less than something else and so forth. Then what if we look at everything that's outside of B? This is not ordered. Well, why don't we just pick something in here? So choose something in here and let that be the next guy after everything in here. And so naturally that thing will be bigger than everything in here. And then we keep listing out from there until, and we do that as far as we do that as much as we can, and we still don't hit everything. So we use the same trick. We take everything that we have ordered and we take the complement in S of, and we just pick something in there. So we pick something outside of what we've ordered and let that be the next guy after everything, after we've tried as hard as we can. And we just keep on going and going. This is the intuitive idea of what a well ordering is. It's the idea that we can put all of S into an ordering if S is going to be well ordered. Now, the principle of well ordering dwells upon the idea of a choice function. The axiom of choice says that there exists a choice function which goes from non-empty subsets so goes from non-empty subsets of S, and it outputs an element of S in such a way that so that if I have a set and it goes into the function, so A is a subset of S, then the output is an element which actually lives in the set itself. So the axiom of choice states that such a choice function exists for every single set, or non-empty set. So this is fundamental, and if we assume this, actually we can build our ordering, because that's what we're doing. We're always choosing something in a set, and so we can build this ordering. So well ordering follows from this choice idea. And essentially, this choice idea is the same thing as equivalent logically to listing out a lot of sets and saying that there's a way of picking an element in each one. That's all it says. It's a fundamental axiom which is put onto the other ones to make arguments tick. It doesn't seem to be followable, or it doesn't seem to follow from any of the other axioms that we usually work with. So it is added in order to make lots of different arguments work. Now, why is well ordering important? Well, one essential feature of a well ordering is that given any subset of a well-ordered set, this guy always has a first, or a smallest, or a minimum. Thinking about this, think about everything that comes before A, or so everything that's less than all the elements in A in the ordering. Now, that set itself, either it has a maximum or it doesn't. If it has a maximum element, the next element over just doing one position, ordinal position next, will actually be the minimum of A. If it doesn't have a maximum, that means there's an ordinal position, which is the first beyond all those. And that particular ordinal position is has to necessarily be an A, because if it was before A, it would be in that, it would actually be over here with the rest of these. So it's actually in A, and it happens to be the minimum of A. So the well ordering, essential property of well ordering is that, in fact, it's actually taken as the definition for well ordered ordering. We have a well ordering on a set if every single subset has a first element. Logically, we can show that every set actually has a well ordering on it. Now, if we take, and this well ordering is determined by a choice function. How do we do it? We simply take everything we've ordered so far, let's call it A, and then the next thing in the ordering is simply the outcome of this. This produces the well ordering. Now, let's suppose that we have two subsets of S. So have a set S, and we have two subsets whose ordering is determined by the choice function, by a choice function that we choose. So there exists a choice function, like by the axiom of choice. So let's take one, and let's suppose that we have two subsets that follow this, meaning they follow that basic rule for how to build the ordering. Well, they both start at the beginning of both of them will be the exact same, namely this, right? Because if you haven't ordered anything yet, this will be the first guy. So they both start in the same place in the ordering. Now, let's try to think about the first thing that's maybe in B that's not in A. Now, if you take the first thing in B that's not in A, we can do that because the set of all things in B that aren't in A, that's a subset of B. And if we assume that B follows an ordering from C, it has a well ordering, so it has a minimum element. So there is a first. Now, if you think about that, let's take the set of all things before that. Those are actually in A itself. And let's suppose also that A actually extends beyond this particular point itself. So it's going to be different. So the ordering, let's just assume that the ordering is different from here to there at some point. Well, that's kind of an issue, because how do you get to so that means the set of all things that have been ordered by this. How do you get to the next one? Well, yeah, there's a set of things that we've ordered so far, and actually since it agrees, well, this is the same thing in both of them, meaning that can't be true. The only way for B to have something that's not an A that follows this ordering is actually for A to be a subset of B. So if you have two different subsets that follow this ordering from C, they're completely comparable. Either one is contained in the other, or the other one's contained in the original one. So if we were to take the union of all these guys that are ordered by C, this itself, so we could actually follows an ordering from C. And the reason why is because if you take 2 points in this union of all these guys that follow the ordering from C, then both of these, well, this one lies in one subset of U, like one of these subsets, and P2 lies in another one, but one of them contains the other one. So that means that both of these happen to lie in one of them that follow this ordering, this well ordering, which means both these are comparable. And so they're ordered. In other words, U is completely well ordered. The union of all these guys is well ordered. Now, the union of all subsets of S that follow the ordering from C is the maximal one that follows the ordering from C. But after we've done that, can we not just choose this this would be like the next guy, and we could actually extend the ordering we have in U beyond. But that contradicts the fact that U is maximal. If we can do such a thing, if there are things in S that are beyond U, which means there is nothing in S beyond U, which means S itself is completely well ordered. So every single set can be well ordered, even the real numbers. Their current ordering is that we usually think about is not a well ordering, because there are plenty of subsets that don't have a first. So we have to change the ordering. We change the ordering according to any arbitrary choice function that corresponds to the real numbers. And based upon that choice function, we can develop a well ordering. Thanks for watching.